Just about there. Sometimes waiting for that final minute is one of the hardest things about teaching. And we made it. Welcome back, folks. We're now about to finish off our very first week of the semester. Just 15 more weeks to go. Well, any questions that people would like to discuss before we get started today? Okay, usually that's how I'm pretty much going to start off each class. If you have any questions, burning questions you'd like to begin with right away, the floor is always yours, and I'll be happy to address those before we start anything else. And for pretty much what we're going to do today, we're going to just do some quick reminders of how the course Canvas page is laid out. And we did make a big promise. We're going to go into the Newton Alta, just Newton for short, homework system so we can take another look. What does problem solving look like inside that system? How to navigate around and those kinds of things. So let's get started, but maybe first before we jump into the Newton system, I also want to mention, particularly if you've just joined the class, and I saw some changes in the roster, some people adding, some people dropping. If you're brand new to the class, maybe you joined it just today, you can see what we discussed all on the very first day of class under here recorded lectures. And our goal is to record every single one of these. They're all just going to fall into that YouTube playlist right there. So that's a link that you might click on quite a bit, maybe for studying exams, or maybe you couldn't make it for a certain day, internet cut out, or something weird might have happened. That's a great way to get caught back up with the course. Other things to take a look at if you just joined is definitely take a look at the syllabus. And nice feature about this class is the textbook is completely free. We'll be working out of this PDF officially. And so when it says we're doing problems in section 2.3, read pages 135 to 146, that's just directly out of this PDF document here, Intermediate Algebra Textbook.pdf. But let's get started then. Everyone had a chance to click on this link from last class period. That was kind of like the big homework assignment. We're try to start out class going as fast as possible. So if you got a chance to get registered in there and you've given a look around, I'd say you're completely caught up. If you haven't done that just yet, you're still in pretty good shape. Give that a try getting registered. And if you run into any snags, please let me know. I'll be happy to help. And anytime you have a question about anything, my email address is right here in the syllabus, or you can just directly email me or message me through Canvas, and I'll be happy to help. So this was the login link. I might want to change the name of this. Well, no, it's just the login. I thought I had registration link. This is used for registration and for logging in all at the same time. So clicking on this again, just click on that button as well. Kind of weird after you click multiple buttons to get somewhere. And it takes you to this Newton Alta page. I already put in my username and password just because I'm prone to forget that stuff. I wanted to get it in before class started. So you missed that page that was going to be there. And this is pretty much the experience. It's not a massively big system. It doesn't contain the textbook. That's the separate PDF. So it's really just a list of problems and due dates. All my due dates here are set to September 4th, and they are in flux. For example, if we don't finish section 2.7 today, we're not trying to race through this material. If we need to come back and do this, finish this on Tuesday, then I move the due dates out further. The due dates, like we mentioned before, are always going to be 1 week from the day that we completely finish off a section. Most sections are going to look like this, just one little module. Occasionally, this was designed by the math department. They decided to split up some of these sections, like 2.7 is split into a couple different sections here and here. This 2.7 we're not trying to get into today. I'm not too sure why it was showing up. The due date would definitely not be September 7th. We're really going to be looking at just these 3 sections here today. So let's just click on the first one. That makes sense to go in order. Actually, let me back up just one page. You might have noticed that there's this blue ring right here, and this ring is partially completed. That's because I did do one problem inside there and submitted it. And so that's kind of our goal, is to get this progress ring to a completely solid circle, and then we've completed that entire assignment. So let me click on this one right here. Our goal is to get our mastery up to 100%. You can click on review instruction, but really there's nothing too massive in here. Maybe view activity details. I'm not too sure what's going on with all this kind of stuff. There is a video. So I guess under activity details, you could dig out videos and things like that just from exploring around. But the major thing you'd be clicking on is either an arrow that says start now or keep going. This one says keep going because I previewed it. So if you were in one you've never clicked on before, let me back up just a little bit. I don't think I clicked on 2.7 just yet. It would say a start arrow, a start indication here already. Some students in the class have already been inside here and trying this out. So if you've been working through these, this might be a little bit boring, but good on you for being proactive. So let me click on section 2.3, click on keep going. They're going to give me that video, so I guess exploring around didn't really matter. They're going to show this to you anyways. And here's the question. If the video helps, it might be a good way to save some time, just looking at what's going on with these kinds of problems. You know, it's not too different than what we did here on this problem right here. But it's good to see things from a different take, a different example, and that kind of thing. Then this is the question. It says, solve the following equation for C. It's kind of odd that this one's multiple choice. Keep in mind, exams themselves are not multiple choice. So there's a definite way you want to do this homework that's going to help you the most on a real exam. So let me show you what I would do if I was a student in this class. I would probably get just ordinary notebook paper, maybe some scratch paper, anything like that.
I think I know which one it is.
Oh, I think that was sorry, was that a question play? That might have been just an open mic. Okay, no worries. So what I would do to do this kind of problem right here is I would open up just some kind of notebook. It's a good idea to have just a common notebook you're going to be doing all your math in. I'm just going to pretend this Word document right here is my notebook. And very first thing you'd want to do is just copy the problem down. It says solve for C. I'll write out 4AB C equals 32. Solve for C. You might not want to write down every single thing here verbatim. Definitely get the question in, what your objective might be, and just start working this as if it was a real problem. Trying to power through by clicking the right multiple choice. I mean, you might be able to eyeball this one and see the solution right away, and that's really awesome. But these get harder and harder as we go. That process gets more and more risky. It's a good idea to pretend this is the real question you're working. You're not doing a multiple choice question. This is more like what it's going to look like on a real exam. Just a problem and a whole bunch of white space for you to solve. You know, this one's not too bad like as compared to the one that we did at the start of the day. So if we're solving for C, our objective is to get C alone. Let me just fix that for the moment. And what we can do is, in one big step, divide out everything that we don't need. C just has to be alone on one side, so we're going to divide by 4, AB, on both sides of the equation. I'm going to use this color here for cancellation. Actually, this looks like a better color. The reason we divide by 4AB is because like factors above and below a numerator will always cancel out. So the 4's cancel out, the A times the B cancels out. C is left alone on the left-hand side. And so we get C equals, let's see, we could write 32 divided by 4AB, but we might lose credit on this question because there's an overall assumption each time we do a problem like this that we're going to also simplify our answers. So we need to do a reduction. 4 can divide into 32. It's going to go inside 8 times. So it cancels here, cancels into 32, leaving behind just an 8. So it looks like our solution, sure, it was one step, but a lot of stuff happened in this one step, right? That's a lot of chicken scratch already. But all that's left is 8 divided by A times B. So that would be our answer on this problem here. I'm going to rewrite for a B, C equals 32, just as a way for me to remind myself that was the original question. And then we started doing this work down below. Well, any questions at all, folks, on solving this one so far? Okay, well, we did it. Our equation is solved for the variable C. Here it is on the left-hand side. Then, again, you're imagining you're doing this on a notebook. Pretend this is my notebook. Once you've got your solution, put it down, and then just take a look at what we have for options. 128 divided by AB, that one's definitely off. And we have this option, C equals 8 divided by AB. Click on that, hit submit. This is the moment of truth. Maybe I made a mistake, we'll find out. And it said, perfect, your hard work is paying off. They get a little silly here with the emote icons and all that kind of stuff. Correct answer is C divided by AB. And all we need to do now is just click on continue. So that's the experience. We go to this through until we get to the very end. If you miss a question, you can keep on trying. You're not going to be penalized for not knowing stuff. It's understood that we're learning this for the first time. So we'll just keep on working through it. If you feel like you keep on hitting snags, don't hesitate to reach out. I'll be happy to help out. If you ever find a problem that just looks like it's just a really hard one, you're not sure how to even start, that maybe the class would like to see solved, you can always start class by saying, hey, Mike, go to your notebook, say what the equation is, and we'll take a look at it and solve it as a class together. I'll always be very happy to start class that way. Well, the moment you hit submit, everything is saved, so you don't have to worry about turning in anything or anything along those lines. And our goal is just to finish out this whole wheel on the current objective, solve a formula for a variable. We'll move to the next objective. And another thing we're trying to do is just fill out this mastery bar to 100%. So these problem sets, depending on the student, you might be solving these pretty quickly, maybe a 45-minute session. If you're a little bit rusty on these, it could take a little bit longer. Don't hesitate to reach out. You can drop into our office hours. You can send me an email asking for help. You can look into the tutoring as well. You know, that's something I forgot to do. Let me actually, just as a reminder for me, I want to post a link on the Canvas page to ISU tutoring, since you can connect even online to tutors from ISU to work on this stuff as well. So let me just write down a reminder. This is important. So we're going to go with all caps on this. I want to post a link to Canvas for ISU tutoring. And so that would be another excellent resource. You can work on one-on-one with the tutor. You do have to put in some of the work on scheduling things out, but students have used that service, get a lot of extra help. As an ISU student, this is completely free as well. Well, that's my demonstration of using the Newton homework system. Any last questions or comments at the moment, folks, before we move on to the course notes? Okay, this one is a Newton example. The reason I'm writing that down is, you know, if we solve an interesting problem, there's no harm in putting it somewhere where we can access it again. So I'm going to take all this, put it in our notes where we solved example 1. We'll solve example B next, but the problem that we just solved, this could be the question you might ask at the start of class. We'll include it in the notes so it's just there, available for everyone. Okay, well, that's our run through and dealing with Newton Alta. If you have any kind of questions on getting set up, working in the system, if you're submitting an answer you feel like is just not being accepted right, let me know and I'll be very happy to work through it with you. There's probably some areas in Newton Alta where it's just tricky to put in answers. So I intend to come back here from here and then throughout the course, maybe not every single day. But if we get into a tricky section, I'll be going back into Newton Alta with you just to show how to enter in certain answers on some of the trickier problems. But that takes us back to right where we were at the start of class. So our next goal is to now just start working through the sections. Our goal for today is to get through these 3 sections here. If we finish off section 2.6, then that would mean we're keeping up with the syllabus. But I'm not going to ever try to race through these sections. It's important material, so we'll take our time with them as we go. Any last questions at all, folks, before we jump back to section 2.3? Okay, let's dive in then. So let me clear all this out. By the way, this section 2.3, this right here, oh, I'm pointing at the wrong thing. This right here is a PDF. And if you open this right now, it's no longer blank. It's showing the work that we did last time. So that's part of what we're going to be doing on the course Canvas page. Everything that we solve is going to be recorded and then just re-uploaded at the end of class. Oh, and one thing I want to remind myself as well as this class goes from 6 to 7:15, and on Thursdays only, I have another class that goes from 7:30 to 8:40. So it's kind of a really short 15-minute transition between the two. We might have some visitors who come in right around 7:10 if they're trying to come to class early. I'll make sure that they're not too big of a distraction, but if they come in and quietly sit down, you may not even notice them too much. If they ever do distract you, if someone comes into the class early, beyond me just telling them they're welcome to sit down, let me know and I'll put in some kind of, maybe we'll just lock the doors so they can't come in. Well, let's get back to where we were left off. This is our big example that we did, our only example that we did last class. We didn't want to put too much on the table since we were only just getting started. And oh, another thing I forgot to mention, there's so much to talk about on a brand new semester. But another thing that I forgot to mention is typically on a Thursday, I'm going to be assigning an additional quiz. That quiz is going to be kind of like a sneak peek on what an exam question is going to look like. It's usually very short because I don't want to compete with the Newton system. But I felt like for this Thursday, I didn't post a quiz only because it's a busy week. We have a lot on our plate. We're getting used to the class. So our very first official quiz will be posted on Thursday's class. I'll make a big deal out of it. We'll talk about how to submit your answers and that kind of stuff. Okay, so that's almost 20 minutes of announcements, but I think we're ready to get started officially. On example 1, the section is pretty short, so I don't have a ton of examples. Example 1, we're just solving a formula for the indicated variable, kind of like the practice problem down here in Newton. Let's do one more. So 3 good examples is a nice one to round out the set. On part B down below here, our next problem, it says solve the equation ax plus by equals c for y. So that means this time y is our target. We need to get this completely isolated on one side of the equation. Let's make sure we have some extra steps to give this a try. Let me first recopy the equation. Ax plus by equals c. Objective is to get that variable y alone. And we can think of this as just an ordinary sequence of steps. What we might like to do is, let's maybe do another preliminary example. We're just starting out the course, so this is kind of a way to get less rusty and see how something like this would go if it was just an ordinary equation. So here is a warm-up example. A nicer equation wouldn't have just an a on the x. Maybe there would just be one number right here, like how about 5 plus, instead of a coefficient b, it would be some other number, maybe 3 Here's the variable y we want to solve for, equals, how about 12, something like that. So solving this equation is highly analogous to solving the one on the left. It's just that we're probably a little bit more familiar with doing this one. Whichever steps we take on the right-hand side, we will duplicate when we go to solve the equation on the left-hand side. So let's give it a start. On the right-hand side, there's a couple ways you could start this. Any volunteers for the first thing you would do?
Maybe subtract y from both sides?
We could try that, but unfortunately, subtracting y from both sides would look a bit like this. Let's write this out just to see what would happen. So if we go 5 plus, now we've subtracted y from both sides. Over here, this would combine down to a 2y equals 12 minus y. So it's not that this was an incorrect step, but in a certain sense, the equation became slightly more challenging, right? These combined as 3y minus 1y for a 2y, but now 12 minus y are unlike terms, they couldn't combine, and we have y on both sides of the equation. So thank you for the suggestion there. It's good to see what this looks like if we try it out. It turns out we probably wouldn't want to do anything with y. We want it to be alone on just one side of the equation. So we want to try out something else as well. Any volunteers for another thing to try?
Take out the 5. So
I agree.
minus 5 for both sides.
Yeah, absolutely. Thank you, Trish. So some people might have said divide by 3. You know, that could work as well, but there's a challenge there. Now you've created fractions through the whole equation. So I like how you said take out 5, just eliminate it. And by take it out, we mean, as you said, if the sign's positive here, we're going to just subtract it off. So subtract 5, subtract 5. So now left-hand side is just 3y. Because of the cancellation, 5 minus 5 is 0. No change over here. Copy down equality. 12 minus 5 takes us down to a positive 7. Looks like I invented a problem involving fractions, but that's okay. Just make sure your fractions are in lowest terms. We'll be reducing some fractions here as well for the practice, and you're well on your way. So notice in order of operations, you're supposed to multiply first, then do additions and subtractions next. But if you're doing equation solving, you kind of reverse the solve. You do these parts right here, subtract first, the opposite of the positive sign. Now, if you have 3 times y, you invert that and do the opposite thing, divide by the 3. Division by 3 allows a cancellation to happen here and here. So now it's just y on the left. We've solved for it now. The right-hand side is 7/3. And the typical way we'd write in the answer is just like that. We wouldn't necessarily put this in the calculator. If we go to, say, a calculator that you're using for the class, maybe something similar to this one, or maybe slightly more advanced, you might put 7/3 in the calculator, but the Newton Alta homework system probably doesn't want this answer unless they specifically said, enter in your answer as a decimal approximation. Usually they'll tell you what decimal place to round to in that case. So we would just ordinarily give it as the improper fraction, 7/3. You don't even need to convert it into a mixed number. So that's what we were going to do on the right-hand side as a warm-up problem. It means on the left, we're really just going to duplicate those same exact steps. Any questions first with what we did on the right? Okay, let's start this out then. First thing we want to do is, again, we want to leave the b alone and the y alone. What we want to do is eliminate this part. However, it's more abstract now, right? It's just ax. They don't give us a value, but we can absolutely still subtract ax from both sides. I would put it under here because they are like terms in that column now. But over here, I might write it slightly off to the side. Because c minus ax are unlike terms, they involve different variables, so I can't combine those coefficients. Then just do a tally. In this column, these both add up to 0, so we don't even have to write down a 0. In fact, it's better that we don't. It's more simplified to just carry down the by equals. Right-hand side is a little bit more challenging if you're a bit rusty in algebra. This will be just c minus ax. And then at this stage, we're almost there. We haven't solved for y, as instructions indicate, unless y is completely alone. There can't be a 3y. That's why we had an extra step here. There can't be a by either. So our next step is just divide by that b, which was analogous to dividing by the 3 over here on the right-hand side. So division by b here has to occur. Division by b here has to occur. Already, even though the homework problem didn't say it exactly, this is similar to a homework problem, there's a general assumption. B cannot be 0 since division by 0 gives us a nonsensical answer, something we'll call undefined. So even though it didn't say anything about the variable b, we have to make that implicit assumption. It's no longer allowed to take on the number 0. So we have now a cancellation of the b and the b on the left, and the equation now just reads y equals c minus ax divided by b. Feels a lot more abstract than the 7/3, but the algebra itself is identical. Well, any last questions, folks, on finalizing part B? Okay, well, let's move on to the next section then. Well, we did a Newton example as well, where we were doing pretty similar things. It was a smaller equation, but it felt more abstract because there's just a whole bunch of stuff you had to work through on the left-hand side. This is what the next grouping of problems is going to look like in section 2.3. The whole section is called solving a formula for a variable, but then there's a couple geometry problems like this one in the set as well. Let's take our time with these, use some problem-solving strategies, and again, this is another great warm-up in getting through Math 1108. So they tell us we have a triangular region. So there's a triangle in the picture. We might as well start to draw one. Well, let's keep on reading through. A triangular region, or just a triangle, has an area of 5.73 square meters and a base of 50 meters. This is a really odd-looking triangle. So imagine a really, really long base, but the area is small, just 5.3 square meters. That's definitely possible, but that would just mean the height of the triangle is really, really short. And that happens to be the question. What is the height of this triangle? It's an interesting question. A huge base, yet a small area, is an odd-looking triangle indeed. But the first thing that we want to do is just draw this triangle. That's weird because to draw it exactly, you'd want to know the height, but that's okay. The only reason we're doing a drawing is because step one to this kind of problem is just include some kind of figure or diagram to organize the formulas so we have a picture to look at that can help us determine what the next steps should be. So for problem-solving strategy, let's write down step one. Draw the figure. We could have said draw the triangle, but it could have been a rectangle, could have been a circle, and so on. So the figure here is going to be a triangle with a really long base. Let's say that's the base. It's 50 meters. And I don't know how high the height is going to be, and this is probably not fully accurate either. Let me try and make it slightly more exaggerated. A little challenging. The height is probably really, really low. Here's my version of that triangle. And again, it's not going to capture exactly what this triangle is going to look like, but it's a way to get started in the problem. The answer to this is when we find out what the height is. So by the height of a triangle, this is what we mean. We go to the base, so this line segment, and we go to the highest point, so way up here, and we're dropping a line vertically downward. Our right triangle, or this little box right here, says this line is vertical or perpendicular with that horizontal line. If you exclude the box, that's okay. It's honestly kind of hard to see everything if we put too much detail in there. So I'll just draw my height this way, kind of a dashed line, and put in h. Our whole job is say what h is. Well, let's now take a look at what the next good logical step should be. We have the figure down. Step 2 would be write down a formula. And you can see the reading in section 2.3 for a slew of these kinds of formulas. This is just a homework problem, so this isn't meant to be something that you're going to see on an exam. If I added exam 2 on a real exam, I would probably just give you the formula so that you're not trying to cram in a whole bunch of random geometry formulas from way back in high school, for example. So for the homework, it's a little bit different. You might have to look it up in the book. You might use Google to just search this out. And the formula that we'd be using is area equals 1/2 base times height. Again, you could find this in the reading, or if you're on a computer, you could go, let's just demonstrate this for the sake of emphasis. Open up a browser, go to Google and just simply ask, or just type in area of a triangle. And they'll tell you right away, area equals, they wrote it in a slightly different way than I would have been. It's base times height divided by 2. They put a little subscript b there, I guess to convey that's the height relative to that base. So those are ways to get those kind of formulas. And if you just get stuck on a problem, you're not sure how to get that formula, you could always email and I'll be happy to help out. Okay, so now that we have the figure, we have the formula, step 3 is going to be make substitutions and solve. A lot of mathematics just happens to be making certain substitutions. So let's read through this problem again. Triangular region has an area of 5.3 square meters. You know, that was some key information right there, because the area is what we'll substitute in for A itself. It also told us the base is 50 meters. Well, what's the base? We mentioned it's this segment right here, so that's the base. And it's lowercase b in the formula right here itself. Our goal is to find the height, so h is going to be the thing we solve for. That means we're making 2 substitutions. We're supplied an area, so it just plugs in right here. We were given a base, so it goes in right there as well. So let's give this a try. I'm going to copy it down below here so we have some ample space to solve. So follow the color coding. In place of the area, we were told A for area is 5.73. It's m squared for square meters if you'd like to put it in. But while I'm solving the equation, I probably would just leave it right in this format, focusing more on the algebra, less on the units for the moment. So then 1/2 times, the base was 50 meters. I'll just put it in as a 50, multiplied by the height, h. So that's the thing we'll be solving for. And you know what? In a certain sense, once we get to here, we're kind of home free. Because if we take a quick peek up above, you'd see we solved some much harder equations. This one's not bad. It's just one variable and a whole bunch of different constants throughout. In solving this equation, some people might multiply both sides by 2. I like that approach because you're clearing the denominator. But if 2 divides into 50 evenly, and it does, that's probably the better approach. So let's just divide right here. 2 goes into itself once, into 50, 25 times. So the whole equation is now reduced to 5.73 equals 25h. Still solving for that h there. Notice this little bit in the instructions. Round your answer to 2 decimal places. Each time you have to do some kind of computation like that, we usually pull up this little calculator here. This is the Desmos link in Canvas. Really is just going to be used for classroom demonstrations. If we ever have to do anything more advanced with the calculator, I'll include some additional graphics to help us learn our calculators in that kind of way. So next step in solving this, just divide by 25. And now we're going to cite our calculator. Well, we already know the right-hand side is done. 25 goes into 25 evenly, so it's just h left over. On the left-hand side, it's 5.73, divide by 25, and we get 0.02292. Let me carry in that exact value. And let me double check my work here. 0.2292. I said that in a weird way, and I confused myself by doing that. Equals h. This is not quite the answer that we wanted. If I scroll out for just a bit, recall we're rounding to 2 decimal places. So let's make that rounding the next step. I ran out of space vertically, so whenever that happens, I'm going to use this official method of just follow the arrows so we get some more additional vertical space. When it sends to round to 2 decimal places, what it means is go to the second decimal place here, check out the integer to the right. It's above 5, so we're going to round this one up. So that will tell us h is equal to, you might write it this way, approximately equal to, and that'd be a great way. You're just being upfront. I've rounded it now. I'll often not worry too much about those matters and just say is equal to 0.23. And at this stage, I probably would bring back the unit. Everything is in meters. So if this is 50 meters long, the height, minuscule, 0.23 meters, a quarter of a meter almost. And that's what makes the area work out just right. We did it, folks. This is basically a word problem, so it's our first word problem of the semester as well. The major emphasis about this problem, sorry, just trying to get this scrolling right. The major emphasis about this problem is really more about just getting through the algebra, this portion right here, and doing the setup. Any questions at all with the solution? Okay. After you get a problem like this, or an answer like this, sometimes you might feel like your number is really off base. I mean, I drew my rectangle height very high just so it'd be a drawing we could see and really work with, but it doesn't look like 0.23 meters. So you might want to do a sanity check, or sometimes this is called a smell test. In other words, just check your answer, see if it really makes sense. Let's do that on the left right here. Check. My check is just going to be returned to the original formula right up here. Area is 1/2 base times height. Let's substitute in the information again. That means area is 1/2 times the base. I'm going to use parentheses now to indicate multiplication. 50 meters times the height. I'll drop the unit and just do 50 and 0.23. Let's put that in the calculator. So I want 1/2 times 50 times 0.23. It comes out as a 5.75. And now we have to decide, well, how do we feel about that? My check says area is 5.75 if the base is 50 and the height is 0.23. But the start of the problem said the area is 5.73. Did we get it wrong, or would you say we're still correct? What could be the explained discrepancy here?
The rounding, you rounded, so that changed the number just that little bit.
Yeah, good call, Dexter. Thanks for mentioning that. So sometimes the check is dangerous, right? That's kind of the issue with this. Like Dexter mentioned, our check would have been perfect if we didn't round, but sometimes these are decimals that don't terminate. Sometimes rounding is a natural thing to do. So when you do your check, just make sure if you have any rounding step, your answer just has to be in the very near ballpark, approximately equal to what the original information was. If it's very, very close, like in our example, we're off by 200ths, that's not too much, then yeah, you probably did all the algebra correct. So don't let the check be a barrier making you think you have to throw all of this out. That'd be throwing out the baby with the bathwater. We're actually on the right track with this one. These problems are bona fide word problems, so we're taking them a little bit slower than we might do other course content. That means if we don't get through all the material that we have slated 2526, that's okay. This is really our very first day getting started with this kind of stuff. But let's give this a try now next on example 3. Unless there's any additional questions or comments about this one. Okay, let's move on to the next then. In example 3, another kind of scenario, we're going to copy the same step-by-step process. We'll draw a figure that matches the information. We'll write down any formulas that seem like they're related to that diagram or picture. And we'll make lots of substitutions. This is, again, a big commonality with these kinds of problems, and solve the whole thing. So here's another clean slate. Let's give this all a try. Let me zoom in a bit on this. Now we're dealing with a rectangle. The length is 8 feet longer than twice the width. So it looks like it's a really long rectangle, not terribly tall. Let's just draw down a rectangle that seems to capture that. We're not going for the exact rectangle that solved this problem. This is just so we can organize all the information. There's lots of moving parts. So we're just giving our brain a mental, like, grappling point, something to grab onto, so we can start organizing all the information. A rectangle has two things, a length and a width. So that gets us started as well. Let's start reading through this again. The length of the rectangle is 8 feet longer than twice the width. This is an interesting statement because now it's relating both length and width together. Let's read this statement right here. The width, W as now highlighted in blue. Now reread this verbatim. The length, L, we might as well color code that, that can't hurt. The length L is 8 feet longer. 8 feet longer just translate to literally add 8. Now it's 8 feet longer than twice the width. If you say twice the width, you're just taking multiplied by 2 against W. Twice is just doubling W, so multiply by 2. And now this is what we would have to have down on this end here. Once you've done this kind of transformation of this sentence down into that line, let's just convey this sentence became that line. It's a good idea to just reread it. L is going to stand for the length. W is going to stand for the width. So if I was to read this verbatim left to right, I would say length is equal to 2 times the width and 8 feet longer. We just want to check, did that make sense? Is that consistent with what this said? Sure, I said it in a slightly different order. I said 2 times the width. That's the same as twice the width. And then I said, and then 8 feet longer. That's just pretty much what is being said right here as well, just in a slightly different way. So now we have this sentence completely accounted for and lots of information now all pulled together in our rectangle. Let's keep on reading through. We're being told the perimeter is 88 feet. That's taking the length plus the length, the width plus the width. In other words, perimeter P is going to be the length twice length, plus the width twice width. And we just happen to know perimeter is 88 feet. So that's this entire sentence accounted for. Next thing says, this is our task for the problem, find the area of the rectangle. So we want a formula for that as well. Area equals, well, just the length times the width. So this is all the information in the problem, and it's kind of weird, right? Sure, it's 3 sentences, but it read in practically just one line, except for a little bit over here. Yet now we have a diagram, we have 2 formulas altogether. All 3 of these objects relayed by both length and width. So this is our setup so far. Now we need to make some substitutions to try to solve for area. This is tricky because the question is about the area. Once we put a number down for A, our job is done. But the only way to put down a number for A is I need a number for L, and we need a number for W, and we have none of that. We have a perimeter instead. So this one's a little bit challenging because we have to go in a really roundabout way to solve this one entirely. So once we get to this stage, let's work with the perimeter. We at least have a number there. Let's rewrite. Perimeter is twice length plus twice width. We can now make some substitutions. In place of P, where the perimeter is, just drop in 88 feet. I'll drop the unit of feet for the moment so we focus on the algebra. Then it's twice whatever L is. But we have a way to write down L. L is 2W plus 8. Let me re-highlight this to emphasize how we're going to substitute. We're going to just throw in that exact expression right in place of L. It's algebraically dangerous because this has 2 different terms. So to get this in just right, we need a set of parentheses to capture 2W plus 8. A set of parentheses, that's supposed to be plural. Then as far as 2W goes, well, we don't have any expression for W, so we'll just carry that down verbatim, plus 2W. Dropping the color coding on that one since we didn't make any kind of substitution whatsoever. And now that's an equation we can work with. We could have substituted L inside of here and put 2W plus 8 times W, but then we're still stuck. That would have been an equation with 2 unknowns, W and the area. There's nowhere to go with that. So that's why we had to go through the perimeter formula first. And the hint is, if they give us the perimeter, it's probably so that we can use it, this formula here first, to get one variable. Now, this is one equation and a variable W. This is solvable for sure. Lots of different things you could do to solve this. I would think that most of us would probably just attack this directly by distributing 2 inside the parentheses. So by the distributive law, we can multiply here to here and say that this is 2 by 2, so 4 times W. That was supposed to be a capital W. It's becoming lower and lower case as I go. Let me fix that. Then 2 times 8 is going to be plus 16, plus 2 times W. So this is the result of the distributive law on the right-hand side. Left-hand side is still just 88. And now next thing we're going to do is combine our like terms. We've been talking about like terms quite a bit. And the way you can identify them is they have the same exact variables, and like terms also have the same exact powers of those variables. These both are power 1, but they both involve W. So we can add them up. The way you might think about this mentally is if you have 4W and you add 2 more W's, you're up to 6W. So we're just adding the coefficients between the 2. Go plus 16 and 88. So we started with an abstract formula up here. Let me scroll just a bit so we can focus on the equation. We made a substitution, and now we have a semi-challenging equation depending on your background. After distributing, it improves after combined like terms. This is a nice equation, kind of like the first problem, that analogy example that we did at the start of class. To solve this for W, first thing you want to do is subtract 16. There you go, it's been subtracted. That will leave 72 on the left-hand side, 6W on the right-hand side. The next thing is divide by 6. And we get 12 equals W. That's part of the mystery. We'll get the area as soon as we know both the width and the length. We happen to know, oh, hang on, let me fix one little thing here. Color coding is no good if you swap the colors midway through the problem, so let's keep that part consistent. Sorry if that was mentally jarring to you, it just smacked me in the brain. So L is green, W is blue. You don't want to change that around in the middle. I get better at this with more practice as we go throughout the semester. So if the width is 12, and by the way, this was in a measurement of feet, so 12 feet, we're about ready to solve for the area. All we need to do is go back over here. This is yet another equation, and we know exactly what W is. We can plug it in right into that spot. So the length is 2 times W. Yet another substitution. Wherever W appears, the moment we nailed it down as being 12 feet, everywhere is 12 feet. It's 12 feet here, it's 12 feet here. So 12 will go in this location as well, plus 8. So now this is 24 plus 8. And that means we're at 32 feet. So 2 expressions down. Width is 12 feet. The length is at 32 feet. We now know everything about this triangle. But you might want to do just a back of the envelope type of calculation to see if we're on the right track. Recall the perimeter is supposed to be 88 feet. That's just the length all the way around. There's lots of ways you could calculate this. Some people might have done it this way. The length is 32 feet plus, the width is 12 feet plus, well, that's another length, 32 feet plus, that's another width, 12 feet plus, and it comes out as 88. That might seem kind of silly, but that's exactly what a perimeter is. Other people might do it differently. Let's go back to the original formula and substitute inside here. Twice length, that's twice 32, plus twice width, that's twice 12. The calculator says it comes out as 88. So that means we have a consistent problem. There's only one way to get perimeter 88 with these two relationships. Length is twice the width plus 8. So now that tells us we're on the right track. Here's where our solution to the problem is going to end up. Area equals, substitute in place of length. Let's see here. It's way over here, then follow the long chain of equalities. This is one reason it's nice to write equalities between your answer as you're doing your work. It has a purpose. It's like a train track. The transitivity property of equality says, if you link up things with equalities, one end is equal to the other end, so we can just drop in 32. Let's throw in the unit there, why not? Then the width from over here is 12 feet. This is still yet another computation, but we're basically there at this point. Our goal is to get area. Now we just go back to our calculator, compute 32 times 12. It's 384 feet squared. If you left off this unit on a quiz or exam problem, I'm not going to worry too much about that. I'm not going to take off points for units. Major reason for that is the homework system Newton itself. It's going to give you a box to put in the 384, and it's going to print the unit themselves. So it's not a fair thing to really try to assess on exam in this course. But occasionally I'll put in the units just for the emphasis. An area should have a unit squared, and that makes sense. Feet times feet would result in the feet squared here. You zoom in a tab. So that's a process on this one. This is one of those problems where we kind of went backwards and forwards throughout the work. We wrote down formulas, we solved the perimeter, then we had to go backwards over here and put in the actual length, then back up here and solve for the area. For these kinds of problems, it might be a good idea to emphasize this is where my answer ended up, because I really didn't do a top-down linear flow the way we wrote down everything. Well, any last questions, folks, on surviving this one? Okay, again, these problems are kind of long. They're a bit challenging. And this is our last one for the day. Although they're a bit challenging, take a look at the ones we've solved in the notes, compare them against the ones you're going to see in the homework. The notes are meant to be a bit of a guide to help you out. There's also very similar examples as well that you're going to see in the reading. So if you get stuck on a homework problem, not a bad idea to just go back to section 2.3 in the textbook and see if there's some related problems that was also solved. Oftentimes there's some pretty similar close problems that can help you out. Well, it looks like we're back to a triangle problem. This is the last question of these notes. And this is one of the problems where we got a bit of a break. They drew the diagram for us, so that's kind of nice of them. There's that rectangular square again. What that's telling us is that this line segment is perpendicular to this one, or in other words, it's a 90-degree angle measurement right here. Or another way to say all that, this is a right triangle.
You
Well,
mean the
if we have
Pythagorean theorem?
Yeah, absolutely. Good call, Clay. If you have a right triangle, this is one of our biggest ideas that are possibly going to help us out. I have to sound this one out. Pythagorean is a person, so we can do possessive. Pythagorean's theorem. Good call on that. So if we see a right triangle, Pythagorean's theorem is going to tell us immediately a squared plus b squared equals c squared. But you know, if we're being honest, that's not exactly all of Pythagorean's theorem. That's just the formula, right? Pythagorean's theorem takes a formula like this, and it tells you how A, B, and C are related. The most critical thing about Pythagorean's theorem is C, the part that's isolated on the right-hand side. Anyone happen to know which segment C should be? It comes with a really funny word, if you remember it from back in the day. It's going to be the length of the another word I have to sound out, hypotenuse. I might have misspelled that, but we're going to let that stand for the night. C is the length of the hypotenuse. Really some interesting words. Pythagorean's a real person, long time ago, thousands of years ago. But the hypotenuse is the longest segment of the triangle. It's always going to be the one that's opposite away from the 90-degree measurement. Or if we draw a right triangle like on this one, it'd be the line that is slanted. That's not a safe thing if we say ever rotated the triangle, that one of those lines could be vertical. Well, the hypotenuse is still, here we go, rotated it like this. Now this is still a vertical line, but you know, that'd be a really odd way to write that problem. So safest thing to think of is the hypotenuse is opposite of the right triangle, so going this way. Or another safer way to think about it is C is always the length of the longest side. So I'll put C right here. It says find the length of the missing side. And that's exactly what C is in this problem. So once we find a value for that, our work is done. You know, they never said what the measurement was. They didn't say this is 60 feet, 60 centimeters, but that's okay. We'll think of this as just units, 60 units, maybe it's miles, maybe it's meters, and so on. Once we get C nailed down, the problem is a little bit safer. Pythagorean's theorem goes a little bit more smoothly. You can call this, say, A or B. It doesn't matter at this point. The algebra will be the same, and so will your solution. I'll go with A equals 11, B equals 60. If you've got it mixed up, you're going to get the same exact answer. So that's how we would probably start off this problem. A is 11, B equals C, B equals 60, and our goal is to solve for C. So let's rewrite Pythagorean's theorem. We have A squared plus B squared equals C squared. So our next step is just to make our substitutions. We know from the diagram A is 11. They just came out and told us right away. So that's kind of nice. So take 11 and square it. Likewise from the diagram, that's a plus sign. Let me fix that. B is 60, so we'll throw in 60. Square that as well. And this would be equal to C squared. So next thing to do, just work these out on the calculator. Let me know if you have any difficulties doing these on the calculator, and I'm happy to give a little bit more guidance on this next step. We want to write out 11 to the power 2. 11 squared comes out as 121. So 121 on this one. Plus, compute 60 squared. Well, if you did this in your head, 6 times 6 is 36. And because you're squaring something with a 0, you'd put in 2 zeros afterwards. But if calculators are allowed on exams, and if this was a real exam problem, this might not be a bad strategy either. And now you're extra sure. 60 squared is 3,600. Equals C squared. Then just add these up. This is going to be 3,721 equals C squared. And our final operation to take is to just take the square root of both sides. So on the left, it's going to be square root of 3,721. On the right-hand side, it's the square root of C squared. And this is something that's going to come back later on in class when we're deeper into the chapters. It's worth mentioning right here. We have a formula that says, well, we'll discuss it later on. This is kind of a preview. But the formula says the square root of A squared. Maybe not A, because we're already using A there. Let's use just an X on this one. The square root of X squared is equal to the absolute value of X. We haven't even done absolute value yet. It's coming up in the next sections, 2.7. But that's a really important formula. It just turns out we're lucky here. We don't need absolute value because a C is the hypotenuse of a triangle. It's automatically positive. So when that variable C is positive, square root and power 2 will cancel each other out, leaving just C itself. The reason to put this on the paper right now is really just as a forewarning. Later on in the course, we will have to pay attention to that. If C was allowed to be negative, we would have needed the absolute values in this. Well, we want to find the length of the missing side. Last thing to do is to take the square root of 3,721. In this calculator, it would look like this. I would type in SQRT, square root symbol comes up, 3,721. And it comes out as an even 61. That's why they didn't ask us to round in this problem. It had an exact answer. So length of the hypotenuse, well, we're really done once we wrote this down. But if you want to, you can complete the diagram and just put a 61 here. It looks kind of satisfying. And our work is done at that stage. This one wasn't so bad because we didn't have to do too much to solve for the equation C. We were done right at that step. But any questions at the moment? Okay, well, we did it, folks. This is the last bit of the notes. One thing I want to mention is some of these problems could be similar to potential exam problems, and you might find yourself in this situation right here on exam, needing to take the square root of 3721. So if you feel like you're a little bit rusty on your calculator, it's a good idea to have your calculator just at the ready on hand while you're following along with class. So that way, if you're punching in your calculator, ready to go, you will have the opportunity to ask questions if you ever hit a snag. And it's a good idea to ask again. Anyone have any questions about the calculator on this one? Okay, well, let's save up these notes. I want to demonstrate what I would typically be doing after class, just to show you what's going on the Canvas web page. What I typically do, this is actually harder on Thursday because I have a class that begins at 7:30, so I have a really tight crunch time. So this might happen sometimes in the morning, Friday morning. I take the file, I convert it into a PDF. There it is as a PDF. I'd close this out and go back to the Canvas course page. Sorry, my words are running together. Not used to talking. It's the first week back in school, and that's like a skill, talking at length all week. I go to this one. This is the one we were just solving, and I remove it from this list. Then we just go to add it back in. Canvas is kind of complicated. We used to be able to just drag and drop things right in. It was so much easier. And it's supposed to allow me to add that in. Hang on, I think my computer is upset with me. Okay, there we go. Add item. And there it is back again. Really just showing that demonstration gives us a bit of a mental break, but to also let you know that this is what's going to happen with each one of these notes. So this set of notes right here now contains all the solutions that we've been working through up to date. And that gives you just an extra resource to see what we did in class. You can refer back to these to see how the problems went. And if I ever forget to do that, let me know. I probably just forgot to do it, get it saved on my thumb drive, and I'll be happy to get that posted. Well, we have some minutes left, looks like just 12 minutes. I want to do just a couple more problems in section 2.5, but I won't take up too much of your time. I'm never going to try to run over too far from 7:15, especially on Thursday. Again, I have a class that starts right at 7:30, back-to-back classes on the last day. This is kind of a preview of what we're going to be getting into in sections 2.5, 2.6, and 2.7. We'll be dealing with inequalities coming up next. So we'll be solving them, and we'll be expressing the solution sets on a real number line and in interval notation. Example one is us really just getting started. Really, it's kind of like a set of formulas that we might refer back to. So when it comes to inequality, we're really going to be solving these ones. I made a change here on the notes to a -3. That's why this one's revised. These are the kinds of things that we want to solve. But before we get to those problems, this is what the solutions are going to look like in inequality form. We'll express these as a plot on the real number line, and this is what it would look like. On the real number line, the solution to an inequality that comes out as x less than -3, it would be plotted in this way. We would drop down a -3 somewhere. You don't have to start at 0 and count off tick marks to -3. You could just make that a bona fide location. And then we would look really carefully at what this is right here. This is a strictly less than sign, which means we would use an open circle right here at the -3. Now, this is saying verbatim, x is less than -3, but this is just another way to say a solution x is to the left of -3. So that means the solution's plot going to the left like this. I'll shade it kind of in this way. And this is now the solution set on the real number line. You don't have to shade the arrow, just looked like it looked a little bit better in that way. So occasionally we'll plot solutions to inequalities when they look like this, in this kind of way, on a real number line. And another thing we'll use quite a lot actually is interval notation. This is actually used in a lot of math classes. So for some people, this might be kind of a reintroduction. This might be a refresher. It could be new to a lot of people as well. I'm going to add one thing that's optional to the number line that you don't have to add. To the very far left is negative infinity. To the very far right is positive infinity, but I'm not putting it on this graph because we're shading exclusively to the left on this one. Now, the reason for doing all of that is when we go to write the answer now in interval notation, it's really just capturing what you see right here on the graph. We'll go from a parenthesis, negative infinity, comma. Instead of shading a line, we'll just put it down as a comma. We're saying we're going to the left forever if we're putting negative infinity, and then we're going right all the way up to -3. And then we put another parenthesis on this end right here. Watch the yellow highlighting. If it's strictly less than 3, we use an open circle, which corresponds to a parenthesis, and it'll be slightly different on part B. Maybe let's do part B next, and we'll make this our final problem so far. We'll come back to this and review it when we come back next Tuesday as well. This is really key information. And it's also recaptured on the notes at the start of section 2.6 as well. So now this one's a little bit different, and the key differences is right here. Verbatim, this is saying x is greater than or equal to 19. So if we were to plot this one out on a real number line, the plot would look like this. We would put 19 somewhere, probably pretty close to the center. But here's the first thing that's new. The open circle was a way to say -3 is not a solution. -3 is not less than -3, it's equal to it. The parenthesis was a way to say we threw away -3, but now 19 is a solution because 19 is equal to 19. So it satisfies the question, is 19 greater than or equal to 19? So the way we say 19 is part of the solution set on a graph is through a solid dot. Now, if we go with greater than, x is to the right of that -19. So now we're shading in this right-hand direction, going off to the positive infinity direction this time. So this is what the graph would look like. And now if we carry it down to interval notation, it would convey like this. Hello. So 19 would go into this spot. Let me actually change that up a little bit there. We would put down a comma and then an infinity. So the change here is from the parenthesis, we threw in this time a bracket. And all these things in yellow track through. If you have a bar that's saying or equal to is a possibility, the solid dot says now the number is included in the solution set, and the bracket says 19 is in your interval. Every number starting at 19 and including 19 solves this inequality. Whereas up here, well, every number less than -3 solves it, but not -3. That one is a non-solution. So we put a parenthesis to omit it and put an open circle to just kick it out of the graph as well. So this is the graph. And the ones below are the interval notation. Any questions about that so far? Okay, well, we went right up to the minute at 7:14. Again, we'll come back to these notes right here when we're back in our Tuesday class, forgetting my schedule, and start working through the notes from here. As far as the homework goes, I have due dates that looked like this. Once we get back in here. But like we mentioned, this is the only one that's official because we actually finished all of section 2.3. The 2.5 due dates, I'm going to move these out so you have the full week to solve these. Well, any last questions at all, folks, before we call it a night and call it a weekend? Okay, well, have a great weekend, folks, and also an awesome Labor Day. We'll be back right here in the notes when we return on Tuesday's class. See you all later.